from where we left off yesterday, which was work, line integrals, work, and particularly conservative vector fields. Could you please keep quiet? Why is the class so small? Is this just the natural attrition of the semester moving on, or is there something big happening at the moment? It's Friday. It is not a rainy Friday. The air is slightly damp. We wish it were a rainy Friday. That's all. It's like, oh, I can feel some cool humidity. I'm going to stay in bed. I should keep my registers for one day when you want me to write you a work reference. And then I look and I go, Fridays? She was never in class. You hear that, people listening to this who weren't present? Okay, I won't actually do that. That would be rather horrible. Okay, conservative vector fields. So what we're going to jump into now is an absolutely marvelous theorem. It's one of those labor-saving things I told you about for conservative vector fields. So, theorem. Let's see. Oh, and by the way, what I'm going to do now, I actually have in a box. It's on page 62. So everything I'm writing now is already typed into your handbook on page 62. So you can copy it down if you want, but it is there. So you can just follow along if you want. Where am I? Let's see. Be a smooth curve given by the vector function r of t. Please keep quiet. Where t goes from some a to some b, whatever they are. Let little f be a differentiable function of 2 or 3, or in fact could be more, but we deal with 2 or 3 variables whose gradient vector, grad f, is continuous on C. Then we have this really rather marvelous expression which says that the line integral along C of grad f is simply the value of little f at one end of the path minus the value of little f at the other end of the path. And this essentially allows us to avoid integrating, because if we're wanting to work out the integral on the left, we can actually just work out the thing on the right and we'll have our answer without having actually integrated. Now, of course, we all love integrating, so who would want to actually avoid integrating? But should you wish to, this formula gives you an opportunity. And what this says is the line integral of a conservative vector field, because that's what grad f is path independent, because it only depends on what the endpoints are, and can be evaluated using only the vector field's potential function. And that's really great. Okay, I'm going to actually prove that theorem for you because it's a nice, quick and easy one to prove. It's a really powerful result that's quick and easy to prove, and those are rare and need to be enjoyed when you encounter them. So, proof. So in fact, let me underline the important part there. The line integral of a conservative vector field is path independent. Proof. Okay. Well, so for the proof, what we're going to do is we're going to start off with the expression on the left, the thing that's got the grad in it, and we're going to do some stuff, and a few lines later we're going to end up with the expression on the right. Okay, so there's the expression on the left. Let's expand that. Okay. I am going to put this into the dt form, so all my various bits in the integral are going to be in terms of t, and my limits of integration are a to b. Now grad f will be full of x's and y's, but I'll replace all the x's and y's and potentially z's with the parametric expressions drawn from my curve equation. So it's going to be grad of f of r of t. So it's still grad f, but it'll be full of t's instead of x's, y's, and z's. And of course, we know that dr with a little arrow on top can actually be written like that. Okay, I showed you that. I can't remember. Was that actually 2 days ago? Okay, so that's a dot product. Let's actually carry out that dot product. Okay, grad f is the vector that you get when you find the derivative of little f with respect to all the variables that it's a function of and cluster them together in a vector form. Let's assume, just for generality here, that f is a 3-variable function. Let's keep it nice and big, but of course it could be 2-variable. That's also fine. So that would be df by dx, df by dy, df by dz, dotted with, okay, r dash is dx by dt, dy by dt, dz by dt. Okay, so let's carry out that dot product. df dx, dx by dt, df dy, dy by dt, plus df dz, dz by dt is a nice mixture of d's there, equals. Now, what is that thing? That big fat integrand full of d's? That should remind you of something. You've seen it before. That's the chain rule. That's the derivative of f with respect to t. Thank you. F is explicitly a function of x and y and z, but x and y and z are functions of t. Therefore, we can calculate the derivative of f with respect to t, because the derivative of something is always how one thing changes as a result of another thing changing. And if t changes, t will change x and y and z. And if x and y and z change, then that'll change f. So f does change if t changes, so df by dt is a legitimate derivative. Okay, and that's chain rule. Hopefully it looks familiar. So now we have an integral of a derivative. You've seen integrals of derivatives before. Let me just write here chain rule. You've seen integrals of derivatives before. You've seen them when you did the fundamental theorem of calculus. The integral of a derivative basically takes you back to where you began. Okay, and that's kind of that's the fundamental theorem of calculus. But particularly, so let's say we have f of x and y and z, and we replace the x and y and z with their parametric expressions. Now we have f as a vector function full of t's. Okay, let's assume that we differentiate it. It'll now be something full of t's. Let's say we integrate it. So we differentiate it and then we integrate it. So we've got f, it's full of t's. We differentiate it, still a function of t. We integrate it with respect to t, still a function of t. We put little square brackets around it, a, b, and then we plug in the a and then we plug in the b. Suddenly there's no t's left. Now what we've got left has got no t's left in it. It's just got a's and b's. So when I say we end up back where we started, that's not quite true. We have little f, we differentiate it, then we integrate it, but it's a definite integral. So we don't end up, it's tempting to just take your thumb and cover up the integral sign and the d by dt and say they cancel each other out and we're left back at little f of r of t. But that's not true, of course, because by the time we get to the end, we've lost t. So in fact, what we've got is f of r of b minus f of r of a, and that was a rather hand-wavy way of me describing the fundamental theorem of calculus. Okay, and if you're not sure exactly what went on there, you need to go back to your roots, as it were, and dig out the fundamental theorem of calculus, which is an incredibly powerful theorem. And not that hard to prove either. You probably did prove it in first year. You may have forgotten, but you probably did, or at least you probably proved some special cases or something. But yeah, the fundamental theorem of calculus basically says that when you're integrating something you're basically anti-differentiating it. And remember how integration is originally defined. Back when you start integration, it's not defined as anti-differentiation. It's defined as area under a curve. And then you can work out area under curve using Riemann sums. And it's a real pain. And the fundamental theorem of calculus says you can avoid this pain by recognizing that integration is actually anti-differentiation. And in the case where your integral, it's a definite integral from a to b, you're not simply anti-differentiating, you're anti-differentiating and then evaluating that antiderivative at the endpoints of your interval. Okay, so that's fundamental theorem of calculus, and that is an incredibly powerful result. I'm going to write this back down here at the bottom and draw a box around it. Very powerful result. And yeah, just one little sentence and then I'll jump into an example. This theorem is extendable. Is extendable to piecewise smooth curves. In other words, C doesn't just have to be a smooth curve. It could actually be a union of smooth curves, a piece of straight line, a piece of circle, a piece of parabola joined together. Piecewise smooth curves. I'm not going to do that, but you can do it. It'll just end up being a sum of integrals. It would be quite easy to prove. By dividing C into finitely, and this is an important word, finitely many smooth curves, and adding the resulting integrals. That finitely many is not something that needs to bother you, but it's something that mathematicians need, because sometimes a certain expression is extendable to more complicated expressions, but as long as the complication is kind of finite in magnitude rather than infinite magnitude. That's not something that bothers us here in this course. Okay, all right, let me demonstrate with an example, and I'm going to do number 14. And I'm going to solve number 14 in 3 ways. As you'll see, it says A, B, C. I'm going to solve the same problem 3 ways. In fact, that is a lie, because the first way is so hard that I'm going to give up. Okay. What have I got? Work done. So we've been given a curve. Here's my curve. E to the t sine t, e to the t cos t. Oh my goodness, how hard can it be? It's only 2-dimensional. This actually must be easy. From 0, 1 to 0 minus e to the pi. And then the vector field that I've been given is 3 plus 2xy x squared minus 3y squared. Okay, cool. All right, so now we want the work done. So the formula for work is work equals, actually get my solutions ready here. There's my work formula. Short and sweet. Okay, so that's going to be F dotted with R dash, okay? And it's not just going to be F, it's going to be F rewritten so that the X's are replaced with their X parametric expression from the curve, and the Y's are rewritten or replaced with their Y parametric expression. Sure, that yawn was so large it almost swallowed me up. Okay, so let's have a look. Have we been given a T? No, we haven't, but let's have a look. In order to get the point 0, 1 out of this curve, I'm going to have to plug in t equals what? T equals 0. T equals 0 will do the trick. If I plug t equals 0 into my R, I will get 0, 1. Yes, I will. Okay, cool. This is t equals what? First component is still 0, but I've got minus e to the pi. So t equals pi, presumably. Yeah, t equals pi will do it. There we go. So my limits of integration are 0 to pi, because they're t values. Because I'm going to have something dt, and so my limits of integration need to be values of the variable that's sitting after the d. Okay, cool. All right, f. Let's write f. But instead of x's and y's, I'm going to replace every x with e to the t sine t and every y with e to the t cos t. Off we go. 3 plus 2 e to the t sine t, e to the t cos t, comma, x squared is e to the t sine t squared minus 3y squared e to the t cos t squared. That's my f, and I still need a dot with r dash.
Okay.
Yeah?
So you don't check if it's a conservative function.
Well, we will. We totally will, and then that'll influence B and C. But what I'm doing here is I'm trying to demonstrate that if you hadn't noticed it was a conservative vector field, you are going into a world of pain. Unless you really like quite complicated integration by parts that covers like 2 or 3 pages. And if you enjoy that sort of thing, then actually you're entertaining a very exciting period. Here we go. All right, R dash. What's R dash? Let's have a look. Each of my components is a product. I'm going to have to use product rule. Product rule says that it's e to the t sine t plus e to the t cos t. Then the other one is e to the t cos t minus e to the t sine t, and then it's dt. And just for somebody following along who's finding this complicated, that is f just rewritten with t's in it, and this thing over here is r dash. Okay, now we've got to dot that. Okay, we know how to do dot products. Dot products is easy. So here we go. Equals. I'm going to write my equals over here because we clearly have a lot of terms. 0 to pi. Let's do the dot products. All right. I'm already getting bored with this. This is 3 e to the t sine t plus 3 e to the t cos t plus 2 e to the 3t sine squared t cos t plus 2 e to the 3t sine t cos squared t plus, okay, everything I've written there is the first component times by the second component. A little bit of distributive law there. 2 terms end up giving me 4 terms. Plus, and then I'm going to dot, I'm going to give up quite soon, okay. That times that, let's have a look. No, hold on. That times that. All right, let me get this right. It's going to be e to the 3t sine squared t cos t minus e to the 3t sine cubed t. Okay, that's a bit of a change. And then I've got a minus 3 e to the 3t cos cubed t, and I've got a minus 3 e to the 3t plus 3 e to the 3t cos squared t sine t close brackets dt. Whew. That's what you get when you do the dot product. Perhaps I've made some careless mistake. I don't think so. But now you've got to integrate that. Okay, all right. So now you're going to integrate. Don't worry, I'm going to give up at this point. But just let me talk you through it. So you're going to have to integrate each term. All right. That first one, can you remember how to do those? When I teach first year, what's it called, integration by parts, I have what I call the ordinary form or something, and the sneaky type, and then the extra sneaky type. And the ordinary is something like x cos x. Okay, that's the ordinary kind. The sneaky kind is like ln x, where you got to put in a 1. Remember those ones? That was the sneaky kind. And then there's the extra sneaky kind, and this is the extra sneaky kind. Because what you do is e to the t doesn't go away. It doesn't matter how many times you differentiate or integrate, you're always stuck with e to the t. That's how exponentials work. Sine doesn't really go away, it changes, but it just changes to cos, and it's not like a polynomial that kind of shrinks as you differentiate it. So with these ones, do you remember what you do? You do integration by parts twice, and you basically end up kind of back where you started, and then you can take it across the equal sign. Remember that? Okay. So that's what you have to do there. But that's the easy term in this whole expression. Well, that one's similar. Okay, so those two are like that. But then we end up with a sine squared cos t. Okay, that'll still be integration by parts. It'll still be integration by parts, but it'll be a harder one. And then the sine cubed and the cos cubed, how do you do those again? Oh, those aren't too bad. Because no, hold on, they are fairly bad. Because what you would do is you'd replace, that's a cube by the way, that squiggle, I'll replace it. You'd replace that with, you'd change it into a cos times a cos squared, and you'd replace the cos squared with 1 minus sine squared, which kind of opens you up for a substitution, except of course this e is still there, and so there's still integration by parts going on, and anyway. So it's not like it's not doable, but see what I mean. It's going to be several pages. You'd probably be well advised to do each term as an absolutely separate calculation and put them all together at the end. Okay. And my solutions that I've typed up, you'll see I've written, good grief, abandon ship. Okay. I give up. I know what to do, but I don't want to do it. Instead, what we do is we say, okay, scroll. Instead, what we do is we say, you know, that was so awful. Let me check to see if f was actually a conservative vector field. What was f again? F was, I've lost it, 3 plus 2xy and x squared minus 3y squared. Okay. Is there a little f such that d by dx of f is 3 plus 2xy and d by dy of f is x squared minus 3y squared? That's the big question. Because if there isn't, we're stuck. We have to do what I started and complete it. That's the only option. That's in that work thingamajig, that work decision tree, that would put us in the top box of the decision tree. No, it's not a closed curve. No, it's not conservative. You'd have to do that work formula, no other option. But we're hoping that f is conservative, so let's give it a look. And let's have a look. That first, if the d by df of f is 3 plus 2xy, that means that little f would have had to have a term 3x. It would have had to have an x squared y term. Okay. If that d by dy of f is what we've been given, I would have had to have an x squared y term. That's convenient. Minus a y cubed term. The 3x term clearly would just be a constant as far as y is concerned, and the minus y cubed would just be a constant as far as x is concerned. So in fact, a little f like this does exist. There is a little f. Big F is a conservative vector field. That little f is, I could add a plus constant, and hence there would be infinitely many potential functions. So it's wrong of me to say that that's the only potential function, but the only way you can embroider on that is by adding a constant. So that's the potential function that we're going to work with. So that theorem that I just proved showed that if you can see your big F as a grad little f, then when you're working out the line integral, you're actually only interested in the endpoints of your integral, the endpoints of your path. Which means it doesn't matter what path you use, you don't have to use that yucky path that we were given full of e's and sines and causes. So let me draw a little picture. We were told it went from 0, 1 to 0 minus e pi. Okay, there's the point 0, 1. Down here somewhere is the point 0 minus e to the pi. And I don't actually know what that other funny path looked like, but we can just choose a different path. And we can just choose that line segment. Try a different path. Because the line integral of a conservative vector field is path independent. It's only the endpoints that matter. It's not how you move between them. So we can come up with a new path. 0, 1 plus t 0 minus 0 minus e to the pi minus 1. In other words, 0 and t element 0 to 1, because the direction vector of my line segment was the entire distance between my 2 points. So that's the different path, and that makes life a lot easier because the r dash of that is not something full of product rule. It's just 0 and minus e to the pi minus 1. So that's the thing that's going to end up going in my dot product. And it's got a 0, which is also nice for dot product. So my work could actually now be, I'm just going to call that C1. Not W. F. Different from the other one that I just called C. So that would be, let's have a look. My values of t that I put in my limits are 0 to 1. F is what f always was, only with the x and the y from r over there plugged into it. So let's have a look. It's 3 plus, well, x is just 0, isn't it? So I know that's just going to be 0. And then 0 squared, that's just also going to be 0, minus 3y squared. Okay, y is a little bit complicated, but not a lot. And we're going to dot that with r dash. And we can even fit it on one line. Just looking at my notes here. Am I disagreeing with my notes? I am disagreeing with my notes. Where have I gone wrong? No, I'm not. No, I'm not. So my notes, I've already squared that out, and here I haven't squared it out. Okay, all right. And so what you can do now is you can square out that thing that needs to be squared, and you can carry out the dot product. And what do we get? We get minus 3 minus e to the pi minus 1 times by 1 minus, did I put the brackets in the wrong place? 1 minus, no I didn't. No, I didn't. We want to square that out. Okay, you'll square that out. That's a trinomial squared. Do you want me to do that? Can I just write dot, dot, dot and give you the answer? Oh, see, we wouldn't actually expect you to do this. We'd expect you to do it the fastest way, which is part C. So, in fact, this question would not be worth very many marks at all. And therefore, if you chose to go this way, the marks would be, even if you got it all right, the marks would be very sparsely scattered across your work. Okay, I'll take the 3 out, and the 1's cancel, and now we want to square. When you square a trinomial, what do you get? You get 1 plus t squared e to the 2 pi plus t squared, and then you get a, let's have a look, minus 2 times that, minus 2 times that, and plus 2. Sorry, it's squashed at the end there. Sorry about that. That's rather ugly. And I did say I'd fix that cube just now. Sorry, I'm just remembering I said that I'd fix that funny looking cubed, and I didn't. Should go back and do that. Let me write this dt over there. Okay, sorry, that's rather scruffy of me. I just ran out of space. You're squaring a trinomial, and if you're uncomfortable squaring a trinomial, then bracket it like it was a line before and do it in steps. But fundamentally, you square each of the terms, and then you get a plus, like you get a plus 2xy when you're squaring x plus y, you get a 2 times each pairing. Okay, I don't want to do this. This is boring. This is polynomials. No, I'm doing dot dot dot. Sorry, I'm mutinied. Sorry. Class isn't a democracy. Don't you wish it was? It's a polynomial. It's a very boring polynomial. It's a polynomial that happens to have e's and pi's in it, but the e's and pi's are just constants. So they're not constants to be scared of. But part C, that's where the angels come out and sing, because we can say that that is just equal to our potential function evaluated at our endpoint minus our potential function evaluated at our beginning point. End point, beginning point. And our potential function, I've scrolled past the potential function, but let's just remind ourselves what it was. It was 3x, was it minus x squared y plus x squared y? I've forgotten now. Plus x squared y minus y cubed. That was the potential function that we came up with just up the page somewhere. Let's evaluate f at that. X is 0, so both the terms that have x's in are just 0. So it's minus e to the pi. Okay. You bring my horrible handwriting under control here. Minus y cubed. So minus y cubed minus plus y cubed. Now that calculation that's at the top of the page there, the alternate path where I used the line segment, it's not a hard calculation. It's kind of dreary, but it's not hard because everything's just polynomials and there's actually quite a lot of zeros, so a lot of terms disappear, and integrating that wouldn't be hard. But it's still several lines. I've written 4 lines up, and that dot 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 probably hides, gosh, at least 1 line, if not 2 or 3, depending how many steps you like to do it in. Whereas this, the entire calculation was just 3 lines. And if I had carried that cos sine thing with all those integration by parts, if I carried that through to its end, it would also have given me this answer. After 3 pages of integration by parts. And a lot of having to go out and buy a packet of chocolate biscuits to get through it. Or whatever it is that gets you through 3 pages of integration. Chocolate's usually good. Okay, so what's the bottom line here? The bottom line here is if you're doing a work calculation and the vector field that's involved in that work calculation is a conservative vector field, it saves you an awful lot of work. In that work decision tree, it means the answer to the second question is if a conservative vector field, that if the answer is yes, it takes you either to box number 2 on that decision tree, which is this thing that we've just done, or it takes you to the very bottom box. Because what if your curve were a closed curve? If your curve were a closed curve, then your beginning point and your end point are the same point. So then your f of r of b minus f of r of a is something subtract itself. And it's 0. And your work done is 0. Boom, just like that. So you can say it's a closed curve, it's a conservative vector field, work done is 0, done, and you can move on, and you don't have to spend 3 pages doing integration by parts. And I think I probably have that here in my notes somewhere. Notice how if C is a closed curve, R of B will equal R, oops, that's rather funny looking. Come on. R of B will equal R of A, and hence work is 0. Okay, according to my little clock, there's 10 minutes left. Why don't you give number 15 a try? What does 15 say? Okay, number 15, exercise 15 looks back at exercise 13, which you did yesterday. 2 of those 3 vector fields given in exercise 13 are conservative and 1 isn't. In fact, let's clear up which is which now. And for those 2 that are conservative, why don't you do essentially what I've just done here in part C, and actually calculate the work done. They've given you a path, but you don't need the path, you only need its endpoints. But let's just clarify in exercise 13. So you try number 15, and it refers to exercise 13 where? It's the middle one that's not.